Hello again everyone, welcome back to ptet.chemistry channel. So this is a continuation of this alternative to practical work. This is work 4 associated with the stoichiometry and mole calculation topic for the O-level or the IGCSE level chemistry, suitable for the 14 to 16 years old chemistry students. If you know what I do on my channel, so do subscribe to my channel by clicking this button on the bottom right hand side. It's all entirely for free in support of this channel and the work that I'm doing. And please share the channel widely with all your friends, chat group, juniors, seniors, relative, and whoever else you think the channel might be useful for. You can also follow me at ptet.chemistry, that is at ptet.chemistry on Facebook, Instagram, and Twitter to get connected and send in your messages and questions, I guess. Alright, so let's get started. In this first question, we have this hydrated sodium carbonate. You might have seen this across various settings, including even alternative to practical number 1 and number 2, if I'm not mistaken. This is a slightly different method in order to work out the water crystallization here, the value of X. And this is using gravimetric analysis. Gravimetric analysis basically means is to do with masses. As this topic has taught you, you can have reacting masses, you can have reacting volumes, whether there's reacting volumes of gases. When we talk about gas collection previously, you can also talk about reacting volumes of solutions. Those are mainly titration. Solution chemistry is mostly about titration. Those will be about reacting volume. Anyway, so this is a setup you have seen in one of my experimental tutorial video, specifically on gravimetric analysis. I did it on copper to sulfate hydrated compound, but this is a similar concept. We use a pipe clear triangle. We have this crucible and this apparatus B, which is used to support the pipe clear triangle as well as the crucible, is a tripod stand. So TRI. So it's a tripod stand, so TRIPOD and then STAND. How can the student be sure that all the water of crystallization has been removed? This is one of the questions, the biggest question we ask in gravimetric analysis. How do we know when it's over? How do we know when it's done? When there's no further change in mass. Because you heat it, you remove the water of crystallization, then all you're left with is just the anhydrous sodium carbonate. How do you know that it's all just anhydrous sodium carbonate when there's no more water being removed? When the reaction is complete, how do you know? When the mass, after you heat it once, you put it on the balance, and then the second time you heat it again, you put it on the balance, then the mass should be constant. So that's what we mean by you should heat the solid until constant mass. So how can the student be sure when there is no further change in mass? When there is no further change in mass, meaning the mass remain constant, but mass of what? Mass of the crucible and the heated content, okay? And the heated contents inside it. Basically, after you heat it, you wait. You heat it a second time, you wait. There should be constant mass, because if the mass is still changing, it means water is still coming off, well, as steam, I guess. On to the next part of the calculations, which is you heated 0.715 gram of this solid. So of course these are contained within the crucible as your container. They have obviously taken away the mass of the crucible. It is actually an important mass that you have to record as you do this experiment, which is the mass of the empty crucible. But anyway, this is the mass of this hydrated solid. You still have this 0.265 of this anhydrous salt that remain. So how much water has been driven out? How much water has been driven out or removed or driven off? So the mass of H2O is going to be the difference between the hydrated salt minus the anhydrous salt. You're going to get 0.45. That is what your calculator shows you, but it shouldn't be what you write down. So this is what your calculator show you. But you know better. You know better because the results given will base on masses that measure up to 3 decimal place. Your mass balance measure up to 3 decimal place. This is calculated, but if you did get to measure it using the same mass balance, you should have it up to 3 decimal place because you're using the exact same mass balance. you don't lose accuracy, you maintain the same level of accuracy as the data that you have been presented. That's what I've been telling you in previous work involving analysis and evaluation, as well as other alternative to practical, as well as other real practical scenarios. Calculate the MR of Na2CO3. You're not given periodic table, so that's why you're given these relative atomic masses here, especially in the context of theory, in the context of alternative to practical or a real practical paper, no periodic table at all. 23 times 2 plus 16 times 1, 23 times 2 plus 12 times 1 plus 16 times 3, I get 106. And this thing actually have a unit of gram per mole because it's the mass for 1 mole of the substance. It's the mass for 1 mole of the substance. So the unit is gram per mole. Just be very careful there. Calculate the relative formula mass for water. So that's just 2 times 1 plus 16 times 1, or could be 1 times 16. It really does not matter because, it's just multiplication. This is just something to make you familiar with the idea. So calculate the mole of sodium carbonate. So mole equal to mass over mR. So the mass there is 265 gram divided by the mR of sodium carbonate, which is 106. So that thing divided by 106. And I get 2.5 times 10 to the minus 3. That is what my calculator show me. I need to be a little bit more appropriate. 1, 2, and 3 significant figure. All this data with 3 significant figure. I should really be appropriate in terms of following through the accuracy of my data. And I should try and label my stuff as best as I can, and I should have a unit in all my working because those are just sensible habit for you to have as part of your training as a science student. So the mole of water here, you're given the mass. So C1 was just basically the mass of water driven off, 0.450, as I said, 3 decimal place based on the accuracy of the mass balance, and then divided by the MR, which you calculated in the previous part of the question. So 0.45 divided by 18, I get 0.025. Again, this is 2 significant figure. So there's 1, there's 2. I should really be consistent and have my answer to 3 significant figure, not because that is always the case, but because that is based on the data that I've used 1, 2, and 3 for this part, 1, 2, and 3 significant figure for this part. So I should try not to lose any accuracy. And just to run up this question, so in this formula unit, this is a balanced formula for this particular compound. So no number in front means this is 1 mole. So 1 mole of these will have X mole of water. So I could say the mole of water over the mole of sodium carbonate from the formula is X mole of water in 1 mole of sodium carbonate, and then equal to the actual amount. The actual amount of sodium carbonate is this is the actual amount of sodium carbonate. I put sodium carbonate at the bottom, so I have to follow through based on my own label. These working are based on your own answer and based on your own handwriting. Of course, you move up the 1, it shouldn't matter because anything multiplied by 1 is just going to be 1 again. And I get x equal to 10. If you don't get this as whole number, you should always run it up to the nearest whole number because that's consistent with water crystallization being a whole number. So that's the end of that first question there. Question 2, this is about lime water. So lime water is a saturated solution. Saturated means it's the maximum amount of these that can dissolve in that solution. That's why we don't call it calcium hydroxide solution. We call it lime water because it's just a saturated solution. Calcium hydroxide, one of the most difficult formula for a lot of students. For whatever reason, I can't comprehend. When we did the lowest common multiple, which is a primary school concept, we're trying to balance out the charges so that, I'm bringing down the value and not the charges. I'm bringing down the value and not the ion. So the value there is 1, you get cross multiplied to the other side. The value there is 2, you get cross multiplied to the other side. What this means is the number of calcium 2 plus ion is 1. The number of OH minus is 2. So what you have is calcium 2 plus, I have 1 of it. OH minus, I have 2 of it. This is equal to calcium OH twice. This is how you pronounce it, calcium OH twice. This is the correct formula for calcium hydroxide. A lot of students, they will make this mistake, as I've seen over the year. That means 1 oxygen, 2 hydrogen. This means 2 oxygen, 2 hydrogen. I'm glad you could count, and you should avoid mistakes like these, which are unnecessary and which will definitely destroy you in the long run unless you start thinking about this kind of methodology as well as the concept of balancing the charges, and this -1 belongs to the whole hydroxide there. Anyway, in an alternative to practical, in any practical, your job is always about the objective. The objective here is find out the mass. You want the mass of calcium hydroxide in 1.00 DNK of lime water. So let's have a look at the instruction. Instructions are always important. Measure this one into a flask. This is most likely using a pipette. So you can think about this in the context of any practical you have done. So you put it into a measuring cylinder because this is pretty accurate. So you want to be accurate using a pipette. Few drops of methyl orange to the flask. Oh no, actually, you want to use a pipette, but they ask you to use measuring cylinder, so that is not accurate at all. This one should have been done with pipette, okay? Not accurate with measuring cylinder. Anyway, this flask here refers to conical flask, which you will have used in titration. And then you put in the hydrochloric acid in the burette, so HCl in the burette, which means your alkali is going to be in your conical flask, and this is methyl orange. So you got to know your methyl orange indicator. It is yellow in alkali, which means in your flask, which is calcium hydroxide, since the burette is containing the acid. And then in acid, methyl orange is going to be red in acid. So you do not want to get up to red. You want it to just be orange, which is your end point. So your end point go from yellow to orange here. You run it through the burette until the mixture changes color. Record the final reading. Repeat it 2 more times. You should always do 1 rough. At least your first thing should be rough. Then you know where you're fishing. You can watch my experimental tutorial video on titration with methyl orange between HCl and OH. Do have a look if you haven't had a look, if you haven't had a chance to do that particular practical. And then 2 or 3 exact titers. And these exact titers should be very close to each other. So these are titration readings based on these, so we don't know which one is rough or not because we are not the one doing it. If we are doing it, then we will have better standards. But since we are already told that someone did it, let's just read the data. This is 0.0 because that's how you read it for the volume on a burette to 1 decimal place, and 1 decimal place is the accepted standard for O-level and IGCSE level chemistry. Of course, when you go to A-levels, you will realize that they do expect 2 decimal place. However, at O-level and IGCSE level, do believe me when I say they just expect you to write 1 decimal place. So here is initial volume at the start, final reading. So when you run the burette, the volume goes down as the volume gets transferred into the conical flask. So you read the burette from top to bottom. This is 11. So this is 11.1, 2, 3, 4, 5. This line is a bit longer, so it's 11.5 because this is 12. So this is 11.6 there. Okay, let's do the same for the rest of these. 11.1, 2, 3, 4, 5. 11.6 is where I start. And now I read this as 23.1, 2, 3, 4, 5, 6, 7. 23.7. The next one, 23.5, 6, and 7. So it seems like this student is just continuing the next titration from the previous one. Final volume, 34.1, 2, 3, 4, 5. A bit longer there. 6, 7, 8, and 9. 34.9. I have noticed that some students thought you are reading this way, but you need to be careful and look at the other readings above and below it and see which direction you're going in. In fact, you're going in this direction. So, you don't read from bottom to top, you read that way around because it's 34, this 35, this 34.9. Pop that into your calculator. So that first one is the easy thing. The second one, I don't want to think so much. I'll just press my calculator. So it's 12.1. 34.9 minus 23.7. You will see that this student, none of them is plus minus 0.2 cm3. So no best title. In fact, this student has done pretty badly in the titration, okay? So this is the maximum accepted margin for the accepted error of margin accepted margin of errors for all level IGCSE titrations. So this student hasn't gotten anything at all. So this thing are called not consistent. And I did identify just now, I said earlier, this student should really have used a pipette because that's what we will have used to transfer the thing that go into the conical flask. We shouldn't use a measuring cylinder. So measuring cylinder is not accurate. So that is the measuring cylinder. And of course, to make it more accurate, we just use what we would normally use, which is the pipette. Of course, they say suggest and they say they don't say the, because if you want, you could also use a burette to transfer. Of course, you would not have the same burette. This burette contains the HCl. You just use another burette, another clean burette, to transfer the alkali, the lime water, into the conical flask, and that's not a big problem. They'll be quite accurate as well, which is why they say rather than the. Okay. Now the student adds the hydrochloric acid drop by drop near the end point. As you know, you want to be careful near the end point. Why is it added drop by drop? We need to be careful. Such that one drop of the HCl from the burette. If you have done this practical with me, you can watch my experimental tutorial video on this titration. You would have seen what I mean exactly. By one drop of this thing from the burette will causes the sudden change in color. The sudden change in color of the solution in the flask, in the conical flask. In this case, it's actually from yellow because you have calcium hydroxide in the conical flask, which is alkaline, and then it will go to orange. So one extra drop of HCl from the burette will go orange, and that is when you stop. If you add a little bit further, one or two more drops, then it will go to red, which is the color of methyl orange in acid. That means you have excess acid already. Okay. And you do it dropwise, obviously, because you don't want to overshoot the endpoint. Okay, because once you pass the endpoint, you can't just go back. Anyway, so the student repeats the whole apparatus, the whole experiment using the more accurate apparatus, this time using the pipette, which is why now you have to take the best titration results. Your best titration results have to be within plus minus 0.2 cm cube. A lot of the times you see alternative to practical papers, their readings are not very accurate. In reality, when you're doing practicals, you are not looking to reach the accepted margin of error. You see, these are error margin. You want your error margin to be as close to zero as possible. So you really want your accurate titer to be as close as possible and not just about reaching the margin of error there. Okay, but anyway, these are within plus minus 0.2. This to this is 0.5 cm cube difference. This and this is 0.3 cm cube difference. So I don't put a tick between any of these, but between these two, because the maximum accepted error margin is 0.2 cm cube for O level and IGCSE level chemistry. I gotta make that clear because if there's an A-level student watching this, then the A-level students will have a different margin error, which is 0.1 cm cube because they are using 2 decimal place. Anyway, forget about that until you reach A-level. Use the tick values to calculate the average volume. So the average volume there of what I tick is 11.8 plus 11.6. Maintain a good habit of using brackets because I do not want you to make a mistake in your calculation. So there's 11.7. Maintain a good habit of writing down the units. So there's 11.7 cm cube units given there. Very quickly, the mole of HCl then, I know the concentration. The concentration is mole per dm cube. The unit is cm cube. When you have n equal to CV, do not forget that your volume has to be in dm cube, and 1 dm cube is 1000 cm cube. So to convert cm cube into dm cube, 1 cm cube is going to be 1 over 1000 dm cube. So 0.100 mole per dm cube has to be multiplied by the volume converted to dm cube. Okay, these are just technical skills. You cannot be good at it one day and then forget about it the other day. So that is mole. I maintain a good habit of writing down my units there. I also maintain a good habit of completing my working. Yes, I do know that I need to fill in the blank. there for my final answer, but I always maintain it a good habit in bookkeeping to write down the value as well as the unit in the working itself. 25 cm lime water is in the conical flask, so this is just basically the mole ratio. This is the base, this is the acid. 1 mole of the base has 2 hydroxide because it's calcium 2 plus, there's 2 OH minus. You need 2 H plus to give you 2 H2O. This is neutralization reaction, very popular in one of the 5 general reactions that you have to know. So the mole of the calcium hydroxide over the mole of HCl equal to 1/2 from the balance equation. 1 mole of calcium hydroxide reacts with 2 mole of HCl. Okay. On the right hand side, there will be my actual mole. The actual mole of HCl is from the previous part of the question. And I want to know the actual mole of the calcium hydroxide that reacted. So a lot of students, they just, they don't like to set up mole equation, mole ratio. I have no idea why. Once I set this up, then there's no way I can go wrong because I can see everything very clearly. Label. And then from the balance equation, the actual amount, provided you can do the math, you can hopefully then see is half times the answer from the previous bit. Or I can say divide by 2, and I'll get this thing straight from my calculator. Do not hesitate to write down standard form because this is the way professional scientists and mathematicians will work. We don't do the one with many zero. The more zero you write, the more confused you become, the more mistake you can make, when you key in your calculator. So make it a good habit of doing things like this as shown on your calculator, but make sure that you can key this into your calculator correctly. Now you have 1 dm cube of lime water. Remember that when you have 1 dm cube of lime water, you are just taking out 25 cm cube. You're just taking out 25 cm cube, and from there, you know the concentration is the same. If the concentration is the same, that means the mole is proportional, directly proportional to the volume. The greater the volume, the greater is the number of mole. So I can say in 25.0 cm cube, I have 5.85 times 10 to the minus 4 mole. Therefore, in 1000 cm cube, how many mole I have? Because this is cm cube, I have to compare with cm cube, otherwise the unit wouldn't match. So there's that times 1000. This is cm cube. The reason of converting the dm cube to cm cube is so that my unit will cancel out there and it will give me mole. These are just simple math, and you have to follow the unit so that you are not lost at all. So this is the amount of mole. It is a lot greater in 1 dm cube because you have a lot more volume in 1 dm cube compared to 25 cm cube there. And we on to the next part. So we know, actually, this one is not related to the other part. So the MR is just 40 times 1 calcium. And I have 2 of these hydroxides. So I have 16 times 1 plus 1 times 1. Should be able to do this as part of your exercise. So if I were you, I would do this bit first. 16 plus 1 is 17, times 2 is 34, then plus 40 times 1, that gives me 74. They have a unit of gram per mole, by the way. So I don't think they'll penalize you if you don't have the unit, but this is defined as the mass for 1 mole of the substance. MR is the mass for 1 mole of the substance. Last but not least, I know the mole in 1 dm cube from the previous part. 0.0234 mole. 0.0234 mole in 1.00 dm cube. I know I have this mass in 1 mole of it. So what do I need? You want your final answer to 2 significant figure. So let me see. Mole equal to mass over mr. So what do I have here? I want the mass in 1.00 dm cube. So I can divide by dm cube both sides. So this is another equation which a lot of students memorize. I'm trying to show you here that, I can get these from scratch. This is mole per dm cube on the left hand side. The right hand side will be gram per dm cube divided by gram per mole. What does this one mean? This means how many mole in 1 dm cube. What does this one mean? The mass in 1 dm cube. I want the mass in 1 dm cube. So this is what I want. Okay, so if I just write this clearly, this is the mass in 1 dm cube. This is the mole in 1 dm cube. This is the mass in 1 mole. So they are all related in terms of the units. So I want the gram per dm cube. I want the mass in 1 dm cube. Mole per dm cube was this one just now, 0.0234 mole per dm cube. Multiply by the MR because I can move this up. So there was 74 in the previous part of the question. So 74 times 0.0234. And I get gram per dm cube. So this is gram per mole. You don't really have to write down the unit like what I've done here. As long as you can do the calculation, I'm sure you'll be all right already. You want it to 2 significant figure. So there's 1 and 2. This one is lesser than 5. We always look at the next one, lesser than 5. So what you have is 1.7 gram per dm cube. This is my unit. How come they don't have gram per dm cube here? Because they already mentioned it, the mass in 1.00 dm cube. So this is the mass in 1 dm cube. 2 significant figure. That's the end of that 12-mark question there. So this question 3 is very similar to one of the question in alternative to practical work 3. There was the preceding work, there was the previous work prior to this ATP4. So you can look back at that tutorial, you can look back at that work if you are very unclear of what I'm talking about here. So what do we have? We have some tablets, but here we have 2 tablets of this iron. Iron tablets, iron supplements. So you have the container plus the tablet, and you have the mass of the container. So the mass of the tablet is going to be the difference between the thing with the container as well as just the mass of the empty container itself. Put that into your calculator. 16.07 minus 11.03, you get 5.04. Do not forget that this is actually the mass of the iron tablet. So maintain the high standard of having units in your working, such that you're just transferring it where the unit's already there. Do make it a habit of writing down unit in your working. Now this iron powder is dissolved in, not iron powder, but this powder contains Fe2+. So you dissolve that powder containing the iron 2+ in excess dilute sulfuric acid, and then you make it out to 250.0 cm cube. You make up a stock solution. So this is something I've talked about earlier, and it's something that you can find in my experimental tutorial video series. So to make it out to 250 cm cube, we use a volumetric flask. For this particular purpose, the capacity or the size that you should be using is a 250.0 cm cube volumetric flask. Of course, then to take out 25.0 cm cube from that thing, so you have 2 tablets of the iron. You make it up to 250 cm cube, and then now you want to just take out 25 cm cube for your titration. So I'm not a very good artist, but what I know is I can draw very simple diagram where I can see here in pink the concentration is the same because I'm taking this up from here, and to take out exactly 25.0 from the volumetric flask, I need to use an apparatus called pipette. So pipette is what I use to withdraw that specific fixed volume, 25.0 cm cube, out from here, where the concentration are exactly the same, but the mole is not the same, because greater volume would mean greater mole, because they both have the same concentration. On the other hand, from here to here, I'm just adding water. For all of these goes into the solution, I'm just adding water. The mole is the same. That's the key thing there. The mole is the same, and that's very important, whereas here the concentration is the same, and that's the important thing there. Solution G is this purple color solution. I talked about it in ATP3. I said that there's another experimental tutorial video on this, so you should have a look at that if you're unfamiliar with what I'm talking about here. You put it into the burette, so your burette is going to look intensely purple. What is going to be the color of the solution when G is just in excess? Basically, one extra drop of this purple color solution. You will get a permanent, so it doesn't go away because it's in excess by 1 drop, so it's a permanent pink color. So it's not a purple color because it's just 1 extra drop, very diluted in the presence of a large amount of water in the solution, but it's going to be so intense that it's gonna discolor the whole thing. Sorry, not discolor, it's gonna color the whole solution to make it a little bit pink, and that pink is a result of MnO4-, which is what you're adding in excess. well, just by one drop, so that you know there's the end point there. You carry out a few titrations here. So you started out from 0.0 because these are burette reading. Burette readings are recorded to 1 decimal place in O level or IGCSE level chemistry. And then your best titer. Your best titer, as we'll talk about later on, you have to take something which do not differ by 0.2 cm³ for your best titer. Ideally speaking, your accurate titer should be as close to 0, or as close to each other as possible with a difference of 0. However, in the case like this, where it is someone else's data, then you need to know how to choose from someone else's data. Here, start from 0.0. So your initial burette reading is 0.0. Your final burette reading 17.1, 2, 3, 4, 5, 6, 7, 8. So 17.8 and not 18.2 because you are reading from the top to the bottom. Hope you can see that the burette is read 17 and 18 there. So it's 17.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. On to the next one. You started from 20, 20.1, 2, 3, and 4. Because I'm reading downwards. Oops, sorry. 20.4 is the initial volume. So be careful where you're filling in the blank. 37.1, 2, 3, 4, and 5. So 37.5. On to the next one. I have 9. This is slightly longer. 9.5, 6, 7, 8, 9, 10. So this is exactly 10. And that would be wrong. It's 10.0 because all these burette reading, including 0, is read to 1 decimal place for your O level or IGCSE level chemistry. Onto the final volume, you have 27, 27.1, 27.2, 27.3. So 27.3. And now to work out the volume. So I have my final volume, I have my initial volume. I need to work out the difference between them. So that gives me 17.8. 37.5 minus 20.4. I get 17.1. 27.3, take away 10.0. I get 17.3. As I mentioned just now, your best titer based on someone else's results have to be within 0.2 cm³. This is your greatest margin of error that's allowed. So it has to be these and these that have a tick, whereas these and these have a difference of 0.7 cm³, way more than the accepted margin of error. These and these 0.5 cm³ difference, way more than the accepted margin of error. I've already done my tick, and now I need to work out my average. Show your working just as well, you want to be sure, use bracket very carefully, and I get 17.2, and you have to make it a habit of writing down units in your working as well to be consistent throughout. So there's 17.2 cm³, the unit is provided there. As with all these kind of questions, they want us to work out the mole. This is the mole of the KMnO4. KMnO4 is basically K plus and the MnO4 minus. So I'll just write the mole of MnO4 minus, which is the same as the mole of KMnO4. Okay. Do I know the concentration? Do we know the concentration? The concentration is 0.0200 mole per DNQ KMnO4. So 0.02. Don't forget 00 mole per dm³, and this is in cm³, so you have to convert that to dm³. One of the biggest danger that a lot of students forget to do. So put that into your calculator, and then you will get 3.44 times 10 to the power minus 4. It has a unit of mole. This is what my calculator showed me. I should leave it in this thing called standard form instead of giving me a number with a lot of 0. The more 0 there is, the highest the chance of me making an error, and it's just a lot of 0 to write. It's better to know this form and how to key this into calculator are very important. Okay. One extra thing you need to be aware of is, I don't know why it went to the previous page. The calculation should have used this concentration there. I mean, it's exact value. No point of looking at the previous page. I should have read the question to begin with. Now you have 1 significant figure, 2 significant figure, 3 significant figure. The number in front doesn't count, so there's 1, 2, and 3 sig fig. Of course, when you key in a calculator, it'll just show you 0.02, obviously. But this is 1, 2, and 3 sig fig, which is consistent with the level accuracy given in the data that we are using. So we should maintain that 3 significant figure because of the data that we have been given. Now we are not given an equation, however, they have given us the relationship. So if I have the mole of iron 2 plus, because that's what I want in my titration, that I pipette out into the conical flask, so is to the mole of the MnO4 minus. They say 5 mole of the iron 2 react with 1 mole of the KMnO4. That is from the balance equation or from the ratio that they give us. This is the actual mole of MnO4 minus the react from the previous part of the question. So based on what I have labeled, I put the MnO4 minus at the bottom, and therefore this answer has to go at the bottom. These things follow whatever you have labeled them. You have gotten it the other way around, then you just have them the other way around because you are reading your own data. So this is the mole of Fe2 plus in 25.0 cm cube of H. So the mole of Fe2 plus in 25.0 cm cube of H, I'll bring that up. So this is divided by that, bring it out to the other side is multiplied by 5. So your answer to the previous part multiplied by 5. Hope you're okay with the mathematics, because, well, to be frank, if you're not okay with these, you're gonna have so much problem with all your calculations. So the unit there is mole. Now that was in 25.0 cm cube of H. Remember that, remember my very simple diagram just now? Where was my simple diagram? My simple diagram was here. I have the mole of H in 25 cm cube. I want the mole here. The concentration is the same, so the greater the volume, the higher is the mole, but the mole is not the same, remember? So I need to multiply by certain factors based on that diagram there previously. So you would have in this 250 cm cube of H, you only take out 25.0 cm cube using pipette, and of course the concentration is the same as N equal to CV. If C is concentration, C is equal to constant, because there is constant concentration, therefore direct proportional, just like in physics, just like in math. So 25 cm cube of H, there was a previous question. I have 1.72 times 10 to the minus 3 mole. So therefore, in 250 cm cube, so I am doing a direct proportion. So I'm trying to work backward, where I have more volume, and therefore I have more mole. So it's a factor of 10, because 250 divided by 25 exactly give me 0.0172. Again, to be appropriate, 1, 2, and 3 significant figure, consistent with the rest of my data. Now, I also know that I have 2 of the iron tablet just now, and I said I'll dissolve all of that in excess dilute sulfuric acid to give me 250 cm cube of these. But I'm not adding iron, so the mole of the iron is the same in both case. I now have the mole of Fe2 plus here, which is equal to the mole of Fe2 plus there. So the mole of the Fe2 plus in solid is equal to the mole of the what am I talking about? The mole of the Fe2 plus in 250 cm cube of H. Now they want the mass of Fe2 plus, mass of Mr. The Mr of Fe2 plus is going to be the same as the Ar for iron atom, because the atom has lost 2 electrons to give you Fe2 plus. Electrons are negligible in mass, about 2,000 times lighter than protons and neutrons, as you have learned in atomic structure back in year 9. Oh wait, you are in year 9, so these are at the beginning of your year 9 syllabus. So move up to 56, and then you can hopefully get the answer. So I'm just going to move on my calculation there. So the mass of Fe2 plus is equal to 56 multiplied by whatever that number is, 0.0172 times 56. Now I get something which is no longer 3 significant figure. I should really round this up to 3 significant figure to be consistent with the appropriate precision or accuracy as governed by the previous data that I've used, as governed by the previous data that I've calculated. Okay. Now using your answers to A and part I, what is the percentage by mass of Fe2 plus? So you use 2 tablet, the mass of the 2 tablet, where was it? 5.04 gram, that's the mass of the 2 tablets, 5.04 gram. So I have 5.04 gram for 2 tablets. It is saying that out of this 5.04 gram, only this much gram is actually iron 2 plus. So what is the percentage of iron by mass? So by mass means out of the total mass, which was 5.04 gram, only 0.963 gram is iron, but I want the percentage, which means my final answer is in percentage. 0.963 divided by 5.04 times 100%, and I get 19.107. I want my final answer to 3 significant figure to be consistent and appropriate with the rest of my data based on the data given. So yeah, I don't come up with the 3 significant figure on my own. Instead, I am basing all this precision accuracy based on the data that have been presented, that I have been given. Okay, so I hope that have been useful. That is actually the end of this tutorial for this alternative to practical number 4, which is the last bit of work, which is associated with this year 9 IGCSE or O-level chemistry calculations topic on stoichiometry, reacting masses, reacting volumes of gases and solution and whatnot. Thank you for watching, and don't forget to click the button on the bottom right to subscribe to the channel, comment the videos, I guess, and yeah, get connected with me on Instagram, Facebook, and Twitter. Send in your questions, send in messages, send in whatever you want. Okay, and I'll see you in the next tutorial video. Thank you for watching.